Thank you very much. And as you see, the title will be dealing with attempts at performing Bayesian inversion on tomographic problems. And of course, somewhere machine learning will enter the game. So this will roughly be the outline. I might probably skip, most likely I will have to skip the task-adapted reconstruction part due to time restrictions, but this is roughly the outline. So a couple of words about tomography first. So essentially that will be the inverse problem that we're going to look at. And tomography roughly means that you're acquiring images of this type. You have some object there. You're interested in what's inside. And you don't want to cut up and open because then the person would not feel so good. So you radiate the person from different directions. And the task is to compute what's inside there. And that's an inverse problem. You can formalize this a bit. So you can, of course, work out the physics of how X-rays interact with tissue. And then you have these typical phenomena here. They might lose energy, which is absorption. They might gain energy, which quite doesn't happen in medical imaging. And they might redistribute energy, which is called the scattering here. And then if you simplify the physics a bit, actually quite a lot, you might write down a physical model for how you're essentially acquiring, you're shooting with a ray of X-rays, and then you're measuring the intensity loss as the X-ray goes through the object or the person in question. So X here is not a coordinate, it's actually an entire function in 3D that describes what you want to reconstruct. And L is the line along which you shoot with the X-ray, so you're measuring this type of line integral, that's your data. So essentially tomographic imaging means that data is a function on a manifold of lines, and which manifold you are dealing with, that depends on your acquisition geometry, your setup or your instrumentation. And then the task is to recover this X, which is the image, essentially modeled by a real-valued function in R3 or R2, if it's a two-dimensional problem. And I'm just going to loosely call this the model parameter. So this is just a model inverse problem, but that's the one that we're going to show examples from. So let's take a couple of steps back and take a look at what is Bayesian inversion in this context. First of all, let's start with the more frequentist view on an inverse problem, or perhaps a more functionalistic view. So an inverse problem, typically, is a very common way of modeling an inverse problem, saying that, or formalizing it. You say that you have what we call the forward model, which is essentially an operator that maps a model parameter, which in tomography is the three-dimensional image, to your data. And data was this function on these lines that you were measuring, right? So this is your forward model. Ideally, you know this thing. If you don't know the forward model, then you're in trouble, right? So ideally, you know the forward model. And your data that you're measuring is a single sample of some random variable. And you can write this random variable as the forward model acting on the ground truth. The X star here means the true image that you want to recover, that you don't know, right? This you don't know. So you're having this one, and then you have some additive readout type of observational noise. That's one. And then the task, of course, is to recover this, or approximate this model parameter, the image, okay? Now, this is the traditional functionality view on an inverse problem, or I would call it perhaps a frequentist view. And the Bayesian view is essentially not a big change. The only change you do is that you allow the images themselves to be represented by a random variable itself. And then there is a prior distribution on top of that you put on the space of images. And then you reformulate the problem and you say that you're not looking for a solution. You're actually looking for the probability distribution of all possible solutions. And of course, in a Bayesian setting, the natural one will be the posterior distribution. And of course, here the data now suddenly is a sample of these conditioned random variables. So you're looking at the probability of the data given conditioned on that you are measuring from this particular object, which you don't know. So the X star here is still unknown, right? So this is essentially, in a nutshell, the Bayesian view. And of course, when you reformulate the problem as recovering a posterior and so on, you would somehow want to relate the posterior to things that you know, like the forward model here or something like that. So, and of course, the most obvious way of doing that would be the Bayes theorem that allows you to do this relation. So here it's expressed in the measure theoretic setting. If you have densities, you can rephrase it in a more readable manner. But roughly, you have the posterior, which is the probability distribution of the model, the images, or the image, or yeah, the images, given the measured data, which is the one that you're looking for. The data likelihood is the statistical model for how data is generated, given an image, which especially would contain your forward model. So in the particular additive noise scenario I was outlining before, you can actually write down the likelihood here, or the measure for the data. It's just the convolution with it's a translation with the forward operator for the noise distribution. And then, of course, there is this prior, right? So I had the data likelihood in green, meaning that you're somehow supposed to know this. Ideally, you should write it down, right? And this is a bit in orange, because sure, you can write down a prior, but it's not equally obvious where you get the prior from. I mean, the likelihood essentially is prescribed by the physics of your imaging. So, of course, you might do approximations and simplifications, but roughly it's given by the experimental setting. The prior is not equally easy to pin down. We'll come back to that issue a bit. And of course, in certain estimators, they might require you to compute this normalization factor that essentially amounts to the probability of data. And I think you're a bit in trouble computationally when you have to compute that guy. So what does then the Bayesian theory for regularization say? If you take a step back and look at what does the mathematical theory tells you from the regularization perspective? So the first thing you, as a mathematician, ask is, of course, is existence an issue here? Now keep in mind now that the goal here is to recover the entire posterior distribution. Right now, I don't care about computational feasibility. This is just theoretically, mathematically, conceptual issues. So we have this, again, we have this condition random variable where the data here is a sample of this condition random variable where the image is the ground truth image, but you don't know that ground truth image. And then you ask yourself, existence. And that essentially means that these conditional distributions exist. And the good news is that they actually do exist under rather weak conditions. So this is not a big issue. You might, of course, ask the next question, is it stable? I mean, is this way of reformulating the inverse problem, does it regularize in one way or another? And since the task is now to recover the entire posterior, you need to talk about what you mean by continuity in the space or the set of probability measures. So there are some results in this direction. So if you pick the Hellinger metric as the one to measure continuity against, then you can actually, with certain assumptions on the data log likelihood of data, you can actually claim that the posterior is continuous with respect to changes in data, which means that you essentially have a regularizing property. So already reformulating the inverse problem, already that step, in some sense, regularizes, which is kind of good news. Another good news is that the moments of the posterior, like the mean, for example, is also stable. They're also continuous. So these are all nice, good news, right? So certain estimators are also regularizing. But that's usually not enough. You also, if you want to talk about regularization theory, you also want somehow that if the data error goes to 0, you somehow want your posterior in this context to concentrate around this ground truth image, right? Now the situation becomes a bit more blurry. There are some results for certain classes of priors. So the scenery is not equally obvious, nice, clean cut and clear. And these type of results are called posterior consistency results. And you might also ask how fast this convergence goes. And these are called so-called contraction rates. So there's a lot of theory that's been developed, and much of this theory actually is quite late, I would say. We're talking maybe 2015 and onwards, especially in the infinite dimensional setting. It's definitely fairly recent work. And much of its aim is actually to show you that the choice of prior doesn't really matter so much. That's the target. Philosophically, you want to say that if you get better and better data, it shouldn't matter so much which prior you choose, right? It should somehow, the influence of the prior should mean less if your data gets better and better, which is kind of makes sense, right? So in an asymptotic regime, the choice of prior is not so central, apart from acting as a regularizer. But this, of course, so this is a typical nice little table. So you have the classical results from functional analytic regularization that you typically have when you pick a paper on total variation or TGV or whatever method you might look at. You have these stability, convergence rates, error estimates. And if there are corresponding notions on the statistical side here. I'm just listing them. What we are unfortunately missing, that, to my knowledge, on the statistical side is what we have in the functional analytics side, is the so-called stability estimates or error estimates. So ideally, we would like to know what happens if you are given a certain data with a certain noise level. Not that data goes to infinity. I mean, not that the noise level goes to zero. That's fine and so on. But what happens if you have a data with a certain bound on the noise? What can we say then? So those results I haven't been able to find. So this is the theory part, right? Now I'm going to be quite quick disclaimer here. So the stuff I'm going to talk about now or sooner, quite soon, with machine learning doesn't really couple to the theory, which is a bit annoying, but that's the case. So I just wanted to give you the theory part that I know about right now. So for how far has the theory gone? So the machine learning part is more engineering-oriented, less mathematical in this sense. But let's look at what estimators people are using then for inverse problems. Obviously, the maximum likelihood is the first choice you could pick, right? It is good in the sense that it doesn't involve some nasty integration or anything like that. Often the likelihood is smooth, so you can address quite large-scale problems. But of course, this is not a regularizing property, so you don't want to use this for ill-posed problems. You might do some early stopping and so on, but nevertheless, this is not what you want to compute if your problem is posed. Well, I would say the next very popular estimator that's in the field is the map estimator. So you simply, but that of course requires you to specify a prior, right? And typically many of these sparsity promoting priors are non-smooth. So typically these optimization problems tend to be a bit harder than the ones for the maximum likelihood. So they are less restricted if we come to really time-critical operations like a clinical CT imaging in a trauma setting. You won't probably be able to run an L1 sparsity promoting regularizer. You don't have the time for doing that. And also, often this is a regularizing scheme, but not always. So it's not equally. Another quite natural estimator would be the conditional mean, right? I mean, why not take the average? That's quite natural to do. Well, the bad thing is that you have to do this integration over all possible 3D images. That's not such an easy thing to do. It also requires you to have the posterior, access to the posterior, which in particular requires you to have access to the prior. So this is definitely unfeasible for, the way I formulate it like that naively is definitely unfeasible for even moderately sized imaging problems. You have to do a lot of tricks. And then of course you have the class of Bayes estimators, where you look at all possible decision rules, which are technically speaking reconstruction methods. So you're optimizing over all possible reconstruction methods. That's the first minimization here. And then you have a notion of what means with the downside of picking a reconstruction method. That's a loss. So here I come with the reconstruction method, and I can compute if it's good or bad. That's what the loss is doing for me. And I'm taking the expected loss. So I'm taking, look at not the worst case, sorry, that's with a different estimator. The expected downside that comes with using this particular reconstruction method. And I'm going to minimize that expected. So this is, of course, obviously this is even worse than the conditional mean. When you look at it, it involves an integration in this expectation. And on top of it, you're also supposed to optimize. So that's even more unfeasible. And interestingly enough, this one is the one that we want to compute, the last one. But we're going to use, of course, machine learning for that purpose. And this is just to write down things a bit more concretely. In the case of when you have additive Gaussian noise, just to show that you might recognize things a bit more easily. If I have additive Gaussian noise, the maximum likelihood would be essentially the least squares type of fitting. And if you take a certain type of class of priors, you might recover or rephrase. A lot of the methods from the functional analytic scheme could be interpreted as a map estimator. But this interpretation is not easily obvious in the infinite dimensional case. There are a lot of subtleties that come in here. So, of course, from the asymptotic theoretical part, as I said, a lot of effort has been gone into saying that the prior is just regularizing, so the particular choice of it might not be so important. It might influence how fast you might contract, but apart from that, this is where kind of it stops. So that's a different philosophy. We're going to adopt the philosophy saying that we want to go beyond. So you can use a prior as a regular ways to stabilize your inverse problem. That's one way of using it. But I claim that you can use it for even further roles. In fact, you can use it to extract more information about your ground truth image. But many common priors that are handcrafted are expressed in terms of this type of Gibbs energies. So you have typically a scalar times the functional here. And I thought of just showing you how some of these look like. So if you do random draws from these priors, and these are commonly occurring functionals that you will find typically in literature. So these are random draws taken from these priors. And here's another one. These are more sophisticated Bezoar space functionals here. And of course, you could ask yourself, I'm going to do medical imaging. And is this a sensible prior to use? If you'd ask a doctor, is that a typical representative image of a human being? Of course, that's not the case. But keep in mind, the prior here is mainly to regularize, right? That's the role of the prior. So this is not as bad as it looks like. When I'm just putting the question like this, it's a bit provocative. But here, the prior is primarily used to regularize. But of course, ideally, if you could have a prior that would generate random samples like that, it feels that it would be more problem adapted, of course. It would be more specific to a certain task. But you also should be able to do a better job, right? So, or this is the upper row is, of course, medical imaging, and the bottom row here is typically what you would see in cryo-electron microscopy, for example, when you have protein complexes. So ideally, we would like to have a prior which is more adapted to the problem at hand. So it has less it generalizes less well, of course, the whole scheme. But it also, when it's applied to the right problem, gives a better result. Clearly, it's not obvious to handcraft the prior that will result in samples of this type. That's obvious. I don't know about that. If anybody knows there, I would gladly listen to that. So the question, of course, is how can we create priors that are better adapted to the problem? And of course, the other issue was, of course, the computational feasibility. So the classical numerical methods, even the recent MCMC techniques that could scale up to maybe even 1 million dimensions and so on, if you look at the really time-critical 3D imaging applications, where you have to have a solution fairly quick, they don't quite make it, right? So many estimators, typically the conditional mean, are still difficult to compute with these classical methods. And also, you usually require some kind of handcrafted prior. So if you combine the two desires that I don't want to handcraft a prior, ideally I want maybe to try to derive it from example data, that's where I'm going to get to, of course. And I want to also have a computationally feasible manner for computing, typically a mean, then this combination is, of course, quite challenging. So the question is, of course, can we use deep learning for addressing these two challenges? So this was spending almost 15 minutes on motivating, where I'm going to get to. So this is one way of doing this is what we call deep direct estimation. So again, this is the initial problem, right? We would like to recover the posterior, but I was just saying that entire posterior might be totally unfeasible to recover. Even though somebody would give it to you, you wouldn't even be able to store it, right? If you take a 3D image, in each voxel, there's a whole probability distribution. It's quite challenging to even store something like that. So we, of course, recast and say we want to compute a suitable estimator. We lower our ambition a bit, or perhaps generating samples from it. We'll come back to that. And then, of course, what estimators are we talking about here, right? So typically, if you're dealing with reconstruction, you would typically compute the mean would be a natural candidate, not the only one, but one natural candidate. You could think if x and y are typically functions, right? Keep in mind, x is an entire function, right? And so is a y. So you can think about the point-wise variance. These are evaluated at each point, and then you square it. If you want to get to some kind of uncertainty in some sense, you could think about, so you can see that you have, depending on what you're choosing before you condition on the y, you can get different type of tasks, or different type of statistical analysis can be performed. So in general, you might have a random variable w, which typically is a function of x and y, right? And depending on the choice of this w, you might get, corresponds to performing different type of analysis associated with the posterior. And then, of course, the question is, can we design a machine learning scheme for computing estimators of this kind? That's what we want to do, right? For the different choices of the w. So rephrasing again, so the task is to compute this estimator of this type, where the w is some suitable. Okay, it's a known combination, right? And we also know that y is equal to, you have the data model here. We don't want to forget about that one yet. I'll come back to that in a second. And of course, I don't want to specify the prior, right? So in some sense, I want to use learning now to learn this mapping. So I want to learn the mapping for each given data that I'm measuring. I'm giving you the data here. I want to compute what this estimator is, okay? And I want to learn that mapping. So that's the point. And at my disposal, I have a lot of training data. I have a bunch of training data, which are samples of this joint random variable, right? That's what I have. Of course, you could, we can simplify a bit here. Let's focus on one type of estimator to make life a bit easier, to be more concrete. So you can take, maybe you put the L2 loss here, just to something more concrete. And then, of course, this is just a remark. This corresponds to computing the conditional mean here. That's a known result. Okay, so then the question is, of course, this is good. So the idea, of course, is that the left-hand side, for you, for you guys, is the left-hand side. The left-hand side expression is, even though it looks very unfeasible right now, is quite well suited for supervised learning. So by the law of large numbers, if I have these samples here, and there are enough of these guys, samples here, that you should, in the limit, as my number of samples increase, they should somehow converge in probability to this expected value. Okay? So I could, with some hand waving, I could say that, well, if I have enough good training data, I might approximate what I really want to compute, this expected value, with this type of expression here. Okay? Well, this is still computationally unfeasible because here I'm really searching over all possible measurable mappings. So keep in mind, the solution to this learning problem is not, that doesn't correspond to one image in tomography. It corresponds to a reconstruction method. So when you're done with training, essentially solving this, or approximately solving this optimization problem, what you have at your hand is a reconstruction method, which you can feed with some measured data and it will give you, return to you back your reconstruction, okay? Now, of course, it's clearly unfeasible to search over all measurable mappings. So here is the first time machine learning enters into the game, right? So you say, okay, I need to pick some parameterized family of operators, and it should preferably have a high model capacity that it can approximate a lot of wide range of phenomena, including nonlinear stuff, but still be computationally feasible, right? That's a kind of a subtle balance. But I'm not talking so much, wait, I'll get back to the architecture here. So you parameterize in this with some suitable neural network architecture, and then this optimization becomes something over a finite dimensional parameter, which suddenly is a bit more feasible, perhaps. It's still unconvex, not convex problem, but. Now the question is, if you go back here, so far this is entirely data-driven. Right? What happened to the A up here, which was my physics knowledge of how my data was generated and all that expert information about my data likelihood. Where did that go? It's gone. I don't talk about that here, right? So the question is there a way for me to encode into this parameterization information about A, this relation up here between X and Y, explicitly? Because the way I formulate it like that now, then I'm essentially learning the forward operator as well, right? And that would require gigantic amounts of training data, which I typically don't have in medical imaging applications. And neither would you have it in many scientific applications. So the task here is to pick an architecture that is a parameterization of these operators that are popping up here, that encodes explicitly the relation that we have up here. Typically, I want to encode the forward operator and preferably also the adjoint of its derivative. These are, by the way, the same components you have when you do a regular variational method, right? Typically. Or other reconstruction methods, by the way, also for that matter. And this brings us to the idea of unrolling. And I want to take 1 minute to make an advertisement for the idea of unrolling because it's quite a fascinating idea. So if you have, in general, forget about tomography now, if you have an operator in general, which is not explicitly defined, but is given typically in terms of an iterative method, and there are many of these. Typically, it could be solution operator to some partial differential equation, or it could be solution operator to some optimization, right? These are all operators. Or it could be even inverse to a certain operator. These are all operators that are explicitly given, they're indirectly defined in terms of some kind of a fixed point iteration, right? Then you might ask the question, I want to approximate this operator now with a neural network. And I want to do it in a way that my neural network picks up certain aspects, not just an arbitrary neural network. I just don't want to put a U-net there and then cross my fingers and hope it's going to work. I want to handcraft a bit properties of this operator I want to approximate. But this is only given implicitly through the iterative method, right? So the idea is, of course, that you look at this iterative method. You typically truncate brutally that iterative method after, let's say, X number of iterations or capital N number of iterations. And then you go in and look at the updates that are taking place and you replace them by learning neural networks. That's the philosophy. And then you keep the other components intact. So I'm going to show you that for the case of the regularized inverse. So let's say, let's start with, we want to look at the inverse of A. Don't care about this being ill-posed now. Just say that we want to do A inverse, right? And I don't have A inverse explicitly written. But I could always argue that, maybe I can relax a bit and say I want to compute a maximum likelihood type of solution, right? So I want to minimize this type of thing here. So typically I would do a gradient descent, right? If A is differentiable. That's the simplest possible idea. Now the thing is that this is supposed to go on for infinity, right? So if I stop this iterates after a few, and when I say capital N, I mean maybe 5 or 10 steps, not several hundreds. Then it doesn't necessarily make sense to do the update exactly like what's been described here in line 2. It doesn't make sense. It only makes sense if you go on forever. So what if I replace this explicit updating with something that is learned, but still depends on the previous iterate and the gradient of the objective here? What if I do that? And that is what we mean by unrolling, right? So we stop after n steps here, and capital N is typically small, and then we replace this explicit update with something with a neural network here itself, but it will take in the previous iterate, and it will take in the entire gradient here, right? And since this thing stops after n iterations, right, it's a well-defined operator. And now, don't make the mistake to think that, but if n is bigger, we will get a better approximation. Because keep in mind, we don't want to necessarily solve this optimization problem, right? We're not interested in that. We actually want to compute the conditional mean, which has nothing to do with this optimization problem. We're just creating an architecture that contains elements that we believe are necessary for constructing an inverse to A. So you might typically say, or you can even break this down further. You can say that you don't want to put the entire gradient here. You can put just the A and A adjoint there, right? That's another way too. So this is a way, schematic way of looking at it. So you have this A operator and A adjoint. If A is linear, we don't have to talk about the derivative. Now we can talk about the adjoint directly. These are handcrafted. They're not learned. They're not trained, right? But then you have these small convolutional neural networks that are in there. So you're feeding your input data, which is Y here. You're feeding your reconstruction candidate. You feed it into this convolutional neural network, but it also gets the inputs from this more handcrafted, non-learned components. Here, capital N is actually 2, right? So and then these could be themselves or might be deep neural networks themselves. So the total number of layers is, of course, capital N times these 2, right? So the whole thing might be deep at the end of the day. So this is, and of course you could do a bit more, you could look at these primal dual schemes instead and let yourself be inspired by them. So typically get something like that. So you could have both A and A adjoint, that is mapping between the data and reconstruction spaces or images. And then you have CNNs that are up there and the CNNs down here. So you get, this entire thing is a big neural network, right? That's the architecture. And now here you have the physics encoded in the A star and A, right? So these are important parts. So this is the idea of unrolling. And this can be used also for solving optimization problems or for other purposes as well. So let's see how this thing performs. Computing the conditional mean by solving this empirical risk problem against the training data. And from that training problem, you get the reconstruction method, which I apply. So this is a 2D CT problem. Let's go fast. I'm running out of time. So, of course, when we do clinical imaging, we don't have the ground truth. That would be like cutting up the patient. We don't want to do that. So what we do is that we take the normal dose CT image reconstruction as the ground truth, And then we take the low-dose CT data, which is the one that you want to now apply your method to. So we don't know about the left-hand side, right? You don't know that. So this is the data. Typically a sinogram looks like that. And your task is from this data to get something which is supposed to be similar to the ground truth, right? That's the task. Now to help you a bit, since you're not a radiologist, just to help you a bit on the way here, I'm highlighting two regions. So you see that slight little dark spot there? So that's actually a blood vessel, but imagine that would be a tumor, for example. So you really want to preserve that guy, right? You don't want to wash it out. And likewise, this region is fairly homogeneous. There's nothing there really. So you don't want to create something that's not supposed to be there. If you create something in medical imaging, then you're dead. You're out of the game. It doesn't matter how good your method is. If it's creating things, you're out of the game. That's the worst thing you can do. It's still more acceptable that you're washing out things, but creating something is really bad. Of course, if you apply to this low-dose data, which is bad data, the filter back projection scheme, which is typically what's in the scanners in the clinic now, if you would have to take a CT scan in a hospital, then this would be the method that would be used. We get something like that. So, of course, this is undersampled and it's noisy, so the doctors will say this is too bad, we'll have to acquire more data. You typically see that you have false features up here that you cannot distinguish from this guy, and you have this streak over here. Now, the doctors are pretty good at knowing these streaks. There's actually a mathematical explanation for why these streaks appear, and they're pretty good at filtering them in their heads, right? So they are trained. So they have a kind of a, joking, you might have a deep learned filter in their heads, right? Biologically, they have been trained for many years. You could try to do some kind of a map estimator with a TV-like prior, assuming that the gradient is sparse. You get something like that, right? So this typically still has the same issue. The false feature here is there, and you have the streak there. So you haven't gained so much. You could apply deep learning as a denoising procedure afterwards. This was the method that won the 2016 low-dose CT challenge. It was the best you could do 2 years ago. It's the same problem. The streak is there, the false feature is there. So honestly speaking, a lot of hard work has gone in here, and you haven't gained so much clinically. Now the question is, what happens if you involve the physics forward operator, the physics of the image the deformation, into the machine learning algorithm with the unrolling scheme that I was just talking about? Well, this is the effect. So by involving the physics into the neural network, instead of just trying to do the neural network independent from how the image is generated, you suddenly actually get rid of these streaks, or you might even still preserve this spot here. So this is something that is more important and goes beyond just PSNR and SSIM type of figures. And of course, you can look at these. Also, the PSNR and SSIM are also good, but more importantly, you actually have new clinical interpretable information. So I just have not many minutes left, so I'm going to go brutally, skip this part and go directly to the, sampling part. So what I was talking about now was that we picked one estimator, right? And then we use machine learning to compute that estimator. By the way, if you want the slides, I'm happy to give them to you. So of course, you might say that, but maybe I don't want to pick an estimator. Maybe I just want the machinery to sample, and then I want to decide afterwards what I want to do. So this brings us to a very classical problem in probability theory. How do you sample from high-dimensional probability distributions? This is a very classical question. And also doing that in a situation where the distribution is not entirely fully known, right? Maybe implicitly given. And we're going to look at GANs for doing that, to try to address that task by GANs. And GANs has been quite a bit in the news. The idea somehow is to pitch two neural networks against each other, one generator and one discriminator. And they have a tendency to generate fairly, in the context of imaging, they can generate very natural-looking images. So here, for example, all the people here in the middle matrix here, which is this region here, they don't really exist. They are known. They don't exist, right? They have been generated by the GAN. And you can actually look at these pictures quite in detail, and you won't see anything unnatural about them. It's actually quite scary. So how does the Wasserstein GAN was mentioned yesterday, in the last seminar yesterday, I think, is one way of setting up a GAN. GAN is, by the way, a variational-based type of scheme where you have a class where you search over class of probability distributions, and you somehow, which is somehow computationally feasible to work with. And among those, you're picking somehow the one that fits best. And the word best is measured by some kind of a distance notion between probability distributions. So here we have some probability measure u, mu, that we don't know. But we, of course, luckily, we have some kind of training data from it. We have samples generated by this thing. And then, of course, we have some way of measuring the distance between this mu, which is unknown, with what I call the generator. So this is a parameterized family of probability distributions, and I'm minimizing this distance. And in the Wasserstein GAN, you're picking the Wasserstein 1 distance. And ideally, you want to pick it so that you're matching this target probability distribution. Well, mu is unknown, so it's not possible to evaluate this expression. So this is kind of meaningless, right? The way I've written it. So there, now you use the fact that you have a Wasserstein 1 distance. So you can use the Kantorovich characterization of the Wasserstein distance. So you introduce the discriminator, which is a one Lifshitz function. And then, of course, how do you ensure the Lifshitz condition pragmatically in a computer program, right? That's not so easy. So there you can do a trick by adding a soft penalty term. I'm now skipping, I'm running out of time. So there is some hand waving here now, sorry for that. But this is still unfeasible because you're really maximizing over all measurable functions here. But of course now you put in here a deep neural network instead, which is a parameterization that is, again, computationally feasible. But we are still not done because this generator is also hard to work with because it's a parameterized family of probability distributions. Yet again, something that's hard to work with in a computer, at least to my knowledge. So what you do here is that you say, okay, we instead write this as a deterministic function with a random input, where this input z has a known probability distribution from which you can sample quickly. And this is finally, and then you finally replace these two expectations, which you cannot compute exactly because you don't have the distributions with the empiric. That's where your training data comes into the game, with the training data here. And this is your final expression that you're trying to solve for these two parameters, right? And to have a word of warning, training GANs is known to be notoriously a tricky problem. So that was also, I think, measured yesterday by Guillermo Shapiro, for example. But this was just to sample from mu, right? Now, my target was to sample from the conditional distribution, the posterior. So, of course, what I said here, you just do it, but for the conditioned one. So you essentially, now you have supervised data instead, pairs, and then you instead have the posterior distribution here. Before you had the mu here, and you can repeat the whole thing here, and you get an expression of this type. I have skipped the penalty term for the Lifshitz, just to simplify things a bit. So in principle, it's not so much different. There's one more difficulty here. That's actually quite a serious issue. In inverse problems, you typically only have one sample for each y. For each, in a CT case, I don't take 10 CT scans of the same guy. That would be like treating the person with radiotherapy. I don't want to do that. So I only have one observation, right? So if I do this up here, I'm going to get what is called mode collapse. I'm going to get generated, which doesn't quite, which degenerates, just gives me the same value. And there's a way around that, which is a bit, actually this is actually quite mathematically well founded, so I'm not going to go into that. I'm running out of time extremely quickly. So all of these details are in the paper, or I can take it offline. But you allow the discriminator to see some more samples, essentially, fictitious samples. So get to the examples here. So here are 5 images. One is the ground truth, the rest are reconstructions. Well, these are easy. That's the filtered back projection. This is total variation. This is conditional mean. Or approximation to conditional mean, maybe I should say, to be a bit more precise, or hopefully approximation to conditional mean. But then we have these two. One is the ground truth, one is the phantom. And it's not so easy to distinguish them, right? The doctors, they need about 20 seconds or something like that in a better screen, not the beamer up here. And then, so they can see that this is the phantom and this is the one sample. But in general, you have the ground truth here. This is, by the way, really bad tomographic data, really bad. And you have the filtered back projection. It really looks bad here. You can't really say so much with it. And of course, you can take one sample from the posterior, right? And this looks good. Right? I mean, this is not so bad, right? No, this is better, right? Well, this is actually quite bad. This is dangerous. This is just one sample from the posterior, right? If I take another one, it's going to look different, right? So of course, presenting a single sample is just odd by itself already. But of course, if you can draw these samples fast enough, then you can maybe compute some kind of a mean from them. So this is computed from 1,000 means, just pointwise, right? You get something like that. Or you could compute the pointwise standard deviation. So you could do things like, if you want to do a covariance type of thing, and so on. And finally, just one example before concluding. This is not the previous one was a simulation still. This is real clinical data. There's no simulation involved. This is 3D imaging. And we are deliberately going to 2% of normal dose. Of course, you wouldn't do that in a clinic. You would take normal dose imaging. But assume your patient comes in, and the question is, there might be a metastasis to the liver. For those of you who don't know where the liver is this large body here, organ here. So there is somewhere there is a small potential cyst or a tumor. And the task is to see if that's the one there, right? And of course, clearly from 2% of the data, or 2% of normal dose, even the most experienced, seasoned radiologists will have no chance of seeing what's going on there. This is truly bad data, right? If you take the conditional mean here, or posterior mean, you get something like that. And if you have a better, on my computer it's actually better visible than on the screen here. The dark spot here is actually more visible on the computer screen. So let's say you suspect that that might be a potential problematic region, and then you can do a histogram of the average intensity inside here with respect to the entire liver. And then you can say that if the averages are sufficiently different, then you say there is an issue there. You could do a kind of a amateurish hypothesis test. And then, then you might, at the end of the day, compare against the normal dose image, which is our ground truth here. We don't have the ground truth, and it actually coincides quite well. If you wonder why these white blobs are there that are not quite visible there, is because we have training data from 9 patients in this whole thing. It's really, really few training data. 9 patients, 3D, right? So some of the patients were apparently given contrast, and some were not. So this is an example of bad training data shining through here. But to conclude, in this example, each sample from the posterior took about 20 milliseconds on a fairly decent gaming PC, something that you could buy if you have you don't have to be a rich person to buy it, right? And the training data was 2,000 pairs of slices like that, taken from 9 patients. So there would be 9 really truly independent, in that sense, data sets. So in that sense, and here is a nice little random walk through the generator. And I think I'm now done. Sorry for jumping over parts, but...
Thank you for this very nice talk. So is there a question?
Thank you for the very nice talk. I have 2 questions. Maybe I missed something in the iterative scheme that you showed. I would like to know typically what is the number n that you have in practice. Yes. And my second question is in your iterative, in your network lambda theta, you want to iteratively improve the reconstruction. How can you? What kind of a supervision you give? What kind of a supervision? How can you supervise the iterative scheme? What kind of ground truth you give to iteratively improve the previous result?
Okay. So the word iteration is a bit dangerous, but I'll try to answer to you. We used, first we started with 10, capital N equals 10. It turned out that we can go down to about 5 or 6 without, big difference. If you want extreme down to 2, then you started suffering. So the capital N here is actually not really related to the iteration actually. I mean, think of it as you're adding layers. So a big N means a big, complex, deep network. With a small n means a shallower network, right? So it's not obvious that a larger N would give you a better approximation necessarily. It might actually make it more difficult for you to train. But there is no good theoretical answer to say Ideally, n is dictated by your time constraints, right? Because the more n you take, the more deep your network becomes, the more evaluations of the forward operator and the back adjoint you have to do. So for us, it was very easy that if you have a time constraint, then that's dictating your capital N. So that's the answer to the first one. The second one is how you train this. So the entire operator that you have, the entire network, is one block operator that maps data to image. That's what it does. Now, of course, you have training data now. Now, what training data do you have? Ideally, you want to have the ground truth and the corresponding tomographic data. Now, in reality, you don't have the ground truth. I mean, that will, again, be cutting up, right? So if you're going to be careful about it, you could do cadavers, like dead animals or something. And then you actually cut up and try to do something. Less effort is that you go to, you take a normal dose image and you say, this is my ground truth. And then I deliberately take bad data because I need to do a difference, right? Otherwise I would be just training to get normal dose image and I wouldn't gain anything. And I forget about the ground truth, of course, and I take the training data. So the pairs of normal dose reconstruction and the corresponding low dose data would be my training data. Yeah, and all of these lambdas there are n of them, capital N of these lambdas. These are all neural networks, they're all trained.
So it's actually end to end. So if you fixed n, if you fixed n to 10, you dictate, and then the training just pass 10 times the same network.
And they won't share weights either. They have their own weights. In our implementation, they do share architecture. They have the same architecture, but they don't share the weights.
Okay, thank you.
Thank you for the talk. As you know, I find this line of research very interesting. In addition to the computational questions of whether you are approximating or how to guarantee or bound the distance between what you get and the approximation, there's an interesting statistical question about, we know that the real data has heavy-tailed features. Like some of the features you can compute that are informative could have heavy-tailed statistics, which plays a big role in compressive sensing. So there's an interesting question about whether there is a posterior mean, there is a posterior standard deviation. We could easily construct scenarios where the posterior mean is not defined.
Well, if that's the case, of course, then you're in trouble.
So I mean, it's really interesting how this, by moving to a very data-driven problem, there's interesting questions of how you would check that the mean exists and stuff like that. I mean,
as I said, we don't have any theory for this that is giving you decent answers to your questions. And for me, it's a motivation to actually sit down and do the theory. Because the performance, at least empirically, is quite remarkable. But the question is, my gut feeling is that this is fairly okay for computing a mean, assuming the mean exists. But it might be, one has to be a bit more careful when it comes to saying that this is uncertainty quantification, because then you have to get the tails in a better manner. And that's, again, a very known, difficult problem in statistics. So I'm sorry that I don't have a better answer than saying that this is for future research.
No, I think these are fundamentally difficult questions.
Yes.
It's not.
Yes, but you're right. If there is even not a posterior mean, then the whole statistical corresponding theory part collapses.
Okay, we can stop here with it. Oh, no. Okay, a quick question.
Thank you for the talk. And I have a question. You showed simulations on 2D images. Does it scale well to 3D images? And what's pretty much the number of parameters estimated? Does it work well?
Okay, quick answer then, because the 2D simulations were 512 squared number of parameters. In that case, the network has 250,000 parameters, 250,000 parameters. The data was about the same size as the image, roughly.
Thank you.
If we can postpone other questions to the lunch break, and thank you again for this.